Hi, I'm Meaghan Podlaski, and this is our work on Towards VR-based early design interaction for electric vertical takeoff and landing, or eVTOL, cyber-physical models. First, just a quick outline of the talk. I'll go through the motivation behind this project, and a quick introduction of the multi-domain eVTOL system, why we chose the modeling language that we did to develop these models, and then I'll explain the eVTOL system in a little bit more detail, explaining the functionalities of all the components, how we can animate them, and the hardware and the loop integration. And then I have a case study for 3 different visualization methods that we looked into using. Physical prototypes of complex multi-domain systems, like eVTOL systems, can be costly and difficult to build. This isn't as much of a problem with those small hobby drones, but when we look into larger eVTOL systems that are on the kilowatt scale, it can be difficult to have multiple iterations of physical prototypes before getting to our final design. Simulation-based studies are using well-understood first principles physics-based models are helpful in early system development. However, determining how humans will react and interact with the system is difficult to integrate with the typical engineering design process. But we can work around this using virtual reality prototypes to interact early into development. This provides flexibility to study and simulate the models with additional human feedback prior to building any physical prototype. If we have problems with the design of the model and the system, we can work those errors out prior to building physical prototypes with VR. Here we have our multi-domain eVTOL model. It comes from an open source Modelica library that consists of multi-domain models for each component. Each engineering domain is modeled, so we have models for the electrical behavior, mechanical behavior, and control behavior, and they're all coupled through physics-based interfaces. The library can be used to model any kind of drone. This includes we have examples for the Otis quadcopter, Mavic Air, and Phantom. Here we are going to be looking at a eVTOL system that is based on the Otis quadcopter. Why did we use Modelica to develop these models and use it for interfacing with VR? Modelica is not a tool, it's a modeling language. Models used with Modelica or developed using Modelica can be used in other tools that implement the same standard language. There's more than 8 of those available. Or these models can be exported using the sister FMI standard and used in other simulation and software tools, which I'll explain more later. Modelica is a language that allows for flexibility. It's equation-based, object-oriented modeling language for cyber-physical systems. The models are both computer and human readable, and there's a strict separation between the model and the simulation and numerical algorithm. Here we have the top view of our eVTOL test system. Inside of that block with the picture of the quadcopter on it, it contains all of the subcomponents that are needed to simulate the eVTOL in the time domain. On the left, we have these blue triangles. Those represent our inputs, which are our desired X, Y, and Z coordinates. The white triangles on the right side of the block are our outputs, which are our actual X, Y, and Z coordinates of the quadcopter. For this example, I have the eVTOL have a constant input for the X and Y direction being held, and then I am giving a ramp in the Z direction command to ramp the quadcopter up to a height of 5 meters over a period of 5 seconds. Going down a level from that block before with the drone in it, we have this system level eVTOL model. So going from the left to the right, the components are, we have our inputs that specify our XYZ location here. And then we have our battery system that will scale the voltage and current applied to the motor depending on the available power and state of charge of the battery. Next, we have our main controller unit, or MCU. This translates the commanded XYZ input to a voltage that will be applied to each motor in the quadcopter. That signal is then sent to this propeller block. The propeller block consists of 3 components: the motors, the rotor, and the blades. So the motor will then spin the blades, and it will also apply a force to the chassis via a mechanical linking between the two components for vertical lift. And then we have our outputs, which are our XYZ coordinates of the eVTOL relative to a point on the chassis, and this comes from this GPS component here. Now that we have our eVTOL model, we can first simulate it to observe the animation as an initial example to make sure that the behavior of the system is working correctly. The eVTOL has been configured to use a 3D object file to represent both the propellers and the body. When we simulate it, we get something like the figure on the right, where an image of our quadcopter pops up. We have our body and our propellers. As we simulate it, we get something like the figure on the left. I have a picture, or I have the plot of the trace of the drone being shown here, where we get the circular movement from the propeller moving, and then we also get some oscillation in the Z direction that's due to the dynamic response of the controller. This is all expected behavior, so we know that our model is working correctly. Now that we have our eVTOL system working correctly, we have to design the interface of the physical controllers with our cyber models. This creates a cyber-physical hardware-in-the-loop interaction with our eVTOL aircraft. So we interface both a joystick and keyboard inputs to translate physical commands into XYZ coordinates, and these are all configured to simulate in real time with user inputs. First, we have our keyboard, which utilizes 6 input commands, positive and negative X, Y, and Z direction. This value is converted into a total output command by determining the difference between the integrated inputs and then passing that through a first order filter. So you'll notice that the inputs have these pink connections here, which represent that it is a Boolean input, where if the key is being pressed, we get a 1. If it's not being pressed, we get a 0. That value is then translated into a real value, where we then can subtract from its other key, because we have one in both the positive and negative direction, and if they're being pressed intermittently, we can get the difference of those prior to applying the command to the system. We also integrated the command using a joystick as well. The joystick has 3 inputs, X, Y, and Z. It's an analog controller, so we don't have to do any of the translation from a Boolean input like we did with the keyboard commands. It works similar to the keyboard commands, where we're taking that input, passing it through an integrator and a first order filter prior to applying that signal to the drone. We have our drone, we have our physical inputs from either the keyboard or the joystick. Now we can simulate the eVTOL model in 3 different VR environments. So we looked into simulating it in DLR visualization library, Unity, and the Unreal Engine. The purpose of doing this in 3 different simulation environments was to stress that these are flexible models. We can interact with multiple environments to utilize the different features available without having to update the model at all. So the DLR visualization library is a proprietary library for Modelica tools. The model will interact in the same simulation environment that the eVTOL was developed in. The model can also be exported via functional mockup unit, which is part of the functional mockup interface, or FMI, to be integrated into Unity or Unreal Engine. The motivation behind this was the FMI standard allows us to solve large-scale integrated modeling and simulation problems by being able to communicate models between multiple simulation tools and analysis tools to utilize the features available without having to redo the model, so it's one model for many tools. A functional mockup unit is a series of header files that consist of the model's equations, variables, and settings, and we are able to co-simulate the model between our old tool, which is the system that we developed the model in, and then the new tool, which would either be Unity or the Unreal Engine, using the old tool's solver. So first, we simulated this in the DLR visualization library. Again, the model and the library share the same development environment. we get our model system shown on the right. These shape components declare CAD files to have the visualization of the drone going through its environment, and then we also have these camera files or camera components that allow us to declare which objects we want to follow within the VR environment. So in this case, we have a camera attached to the chassis of the drone. So as we go through the environment, we are following the drone. So when we simulate it, we get something like the figure on the bottom right. One of the co-authors, Jake, has the headset on for the VR. The drone is moving inside of that headset, and you can see everything that is on the computer screen inside of that. And then we're also just showing it on the computer screen for proof of concept. As he's pressing the keys on the keyboard, the drone moves around the environment. So we get this, because we're using this method, the big benefit of this is we avoid any issues with model synchronization, which we'll show in a bit. And in future development with this method, we want to include a more detailed version of the model. So we want to add collision interaction with the environment, and we want to have a more mature model for the drone where we have separately spinning propellers from the chassis instead of just one lumped model like we have right now. So we have the model simulating in the same development environment that we made the model in, and now we're exporting it to both Unreal Engine and Unity. So in Unreal Engine, we used an open source plugin to import the FMU from the into another VR environment. All the mathematical attributes of the eVTOL model are now imported into Unreal Engine. We get a figure like the one on the bottom of the screen. This is a representation of the drone. It's just using a placeholder image right now. In the future, we will add a real image of a drone, but we had some challenges that delayed all of that. Since the model is being communicated between two different software tools, we had difficulty simulating the model in real time. It required us to update the solver and play around with the solver settings so that the model would update the location variables in real time, which now we're getting based on these updated variables on the right, which track the drone moving through the environment. Also, utilizing an open source plugin made it difficult to reliably simulate the model. There were some bugs within that plugin, so we had to work around that as well. Our next steps with this is to improve the visuals of the drone instead of just using this placeholder circular stone image. We also simulated the drone in Unity. Again, we exported the model as an FMU, imported it into Unity. We can control the drone in Unity using either keyboard commands or the joystick gaming controller. Our main obstacles with this method was, again, we had difficulties obtaining consistent time synchronization between the Unity game engine and our FMU. The FMU requires real-time simulation to properly control the drone because of our hardware-in-the-loop inputs, and we would get sometimes a lag between the communication of the two softwares. So we had to work around that to prevent the model from reaching an unstable state. Now that we've worked past that, our next steps would be to, again, include a more rich model for visualization, like separately controlling the drone's propellers from the body, possibly including collision detection, but there might be some limitations with the gaming engine itself. Okay, so in conclusion, we have produced a method where we can produce models for flexible purposes, meaning we have one model and we can use it in multiple tools. So the FMI standard allows us to use the same model that I showed in multiple VR environments and tools without having to alter or reconfigure the model, with the exception of changing some minor solver settings. We didn't have to update any of the model variables or the model structure at all. It was just one model. This lays down a proof of concept of how models can be integrated into VR environments at early design phases without substantial investments. The only things that we invested into this was to pay for the licensing for some softwares. Other than that, we didn't have to do anything crazy investment-wise. And this can all be leveraged in the future to facilitate design methodologies where the designer and end user can gather feedbacks on requirements and specifications related to human interaction that are difficult to capture today. In the future, we plan to improve the visualization quality and interaction of the drone in its environment. So we have one lumped model right now for the drone in all of the visualization environments where it's just the whole body, the propellers don't spin independently. We want to get something more dynamic like what we saw in the animation case. We also want to include collision detection in cases where we can control multiple drones in one environment so that we can watch it interact with the environment subject to the laws of physics. However, this may be difficult since gaming engines typically don't do this. Okay, that is all. So I will take any questions. Thanks for your attention.